Take a regular steel nail. It weighs just a few grams, but if you drop it in water, it sinks instantly. Intuition tells us that's how it should be because iron is heavy. Now look at a modern cruise ship. It's a steel mountain as tall as a 20-story building. The weight of such a giant can reach 200,000 tons. That's millions of nails melted into thick hull plates and huge engines. By everyday logic, this colossal mass of metal should sink instantly. After all, the material is the same. Steel. The density of steel is 7,800 kilograms per cubic meter, while water is only 1,000. Steel is almost 8 times heavier than water, but the giant ship doesn't sink. It confidently carries thousands of passengers and thousands of tons of cargo. This is the maritime paradox. Why does a tiny piece of metal sink in a glass, but a metal structure weighing 200,000 tons does not? There's no magic here. There are only strict laws of physics, which we'll explain now. To find the answer, let's go back to the 3rd century BC, to Syracuse. It was there that Archimedes formulated the law of hydrostatics. Legend has it that he understood this while taking a bath. His body displaced water and it overflowed. Archimedes' principle is the foundation of all shipbuilding. It states, a body immersed in a fluid experiences an upward force. When you lower an object, it needs space. It pushes the water aside. The water resists and pushes the object from below. The strength of this push depends not on the material of the object but solely on the weight of the water displaced by the object. If the object's weight is greater than the weight of the water it displaces, it sinks. If less, it floats. Archimedes gave us the main tool. To understand if something will float, compare the mass of that something with the mass of water of the same volume. Remember the childhood riddle. What's heavier, a kilogram of lead or a kilogram of feathers? They weigh the same, but in water, lead will sink, while a bag of feathers will float. The answer lies in density, the amount of substance in a unit of volume. Imagine density as passengers on a bus. Wood is like a half-empty bus. Molecules are far apart. A kilogram of wood takes up a large volume. Steel is like a bus during rush hour. Molecules are tightly packed. A kilogram of steel is a very small, compact object. Back to water. A wooden cube weighing 1 kilogram is large. It displaces a lot of water, let's say 2 kilograms. The water pushes it up more strongly than gravity pulls it down. It floats. A steel nail is very dense and compact. It takes up little space and displaces a tiny amount of water. The weight of the displaced water is much less than the secret is that engineers change the average density of the structure. Engineers solve the problem with geometry. Roll a piece of foil into a tight ball and drop it in water. It'll probably sink. Make a boat out of the same piece of foil. It'll float. The weight of the foil hasn't changed, but now we're submerging a structure of aluminum plus air. The ship's sides create a huge internal volume. Look at a supertanker in cross-section. Thin steel hull, structural frame, and giant voids. Holds, cabins, engine rooms. From a physics perspective, a ship is a steel bubble with air. The density of steel is huge, but the density of air is negligible. If you add the mass of the steel and the mass of the air inside, then divide by the total volume of the ship, you get the average density, and it's less than the density of water. To the ocean, a 200,000-ton ship isn't a dense brick, but a lightweight structure, like foam. The water doesn't care what the shell is made of. It only cares that the object as a whole is lighter than the water it displaces. But just floating isn't enough. A log floats too, but it's hard to stand on. It rolls. A ship must be stable, return to an even position after tilting. Here, 2 points of force work. The center of gravity, where the ship's weight is concentrated, and the center of buoyancy. When the wind tilts the ship, the underwater shape changes. One side goes into the water, the other rises. The center of water pressure shifts toward the tilt and starts pushing the ship back. A lever forms, setting the ship straight. The main rule for engineers: heavy things should be at the bottom. Engines, fuel, and generators are located at the very bottom. Upper decks are made of lightweight materials. It's like a roly-poly toy. The heavy base keeps the toy from tipping over. If the ship is empty, it floats too high and loses stability. To prevent this, ballast, thousands of tons of seawater, is pumped into the double bottom. It acts like an anchor, lowering the center of gravity. How does the captain know how much cargo can be taken on board? Each ship has a special mark, a circle crossed by a line, with a scale of letters next to it. This is the Plimsoll line. These marks appeared in the 19th century to stop greedy ship owners from sending overloaded, floating coffins on voyages. The scale is needed because water density changes. Salt water is denser than fresh water and supports the ship better. Cold water is denser than warm water. That's why international markings are used. S, summer, summer. Baseline, W, winter, winter. The ship should be lighter to have a reserve of freeboard. Shows how much the ship will sink if it enters a river from the sea. These lines guarantee a reserve of buoyancy, a sealed volume of air above the water that will save the ship in a critical situation. Disaster strikes when the seal is broken. If the ship gets a hole, water rushes in, displacing air. Each cubic meter of air weighs just 1 kilogram. Each cubic meter of incoming water weighs 1,000 kilograms. The ship's mass increases rapidly. Once the average density of the ship exceeds the density of water, it turns into that nail and sinks. Another danger is water on the deck or in a wide hold. When tilting, it spills to one side, sharply shifting the center of gravity. The ship can capsize, turn over, even before it loses buoyancy. The principle of compartmentalization is used for protection. Inside, the hull resembles an ice cube tray. Watertight bulkheads divide the space into compartments. If one compartment floods, the water doesn't spread further. The ship becomes heavier, sinks lower, but stays afloat thanks to the air in the remaining dry compartments. The sinking of the Titanic is a harsh lesson in physics. The iceberg damaged too many compartments. The ship's bow became so heavy that it went deep down. The ship tilted forward, and water began to spill over the top edge of the bulkheads into the next dry compartments. The bulkheads weren't sealed at the top, and supertankers carry hundreds of thousands of tons of oil. Their wide hulls act like giant barges, distributing the enormous weight over a vast area of water. Cruise liners as tall as skyscrapers remain stable thanks to lightweight aluminum superstructures and heavy bottoms with active roll stabilizers. Floating factories weighing 600,000 tons stand in the open ocean for years, rotating around a giant axis to face the wind and reduce stress on the hull. So why does a nail sink? Because it's a solid piece of metal. It's too compact and can't displace enough water to offset its weight. But a ship is a smart combination of steel and air. Engineers don't argue with the laws of nature. They use them. It's this deep understanding of physics that allows thousands of tons of steel to float above the abyss as easily as a feather in the air.